Hi, my name is Polhill, and I'm going to talk to you about large-scale agent-based social simulation. Brief outline of the talk. I'm just going to give you a little bit of an introduction to agent-based social simulation, and then talk about why doing agent-based social simulation on a single computing node imposes constraints that matter, which leads into a discussion of large-scale social simulation, and a question which, to some extent, Paul Watson answered: why don't we use the cloud? It's a pretty obvious solution. So, agent-based social simulation has various origins, including complex systems, which have kind of been touched on briefly in the previous talk, but some of the insights from complex systems theory are that the heterogeneity of individuals, their differences and the interactions among them actually matter for how the system plays out over time. Others might disagree with that summary of complex systems, but that's mine. There are some sort of disaffected economists who are dissatisfied with what they call the Homo economicus model of human decision making. Now, if you're an economist, a full, hardcore, traditional economist, that is, rather than perhaps more modern economist, you believe that when people buy things, you have instant knowledge of everything else you could spend that money on, and infinite computing power to make the optimum decision. And in fact, as soon as you go a little bit away from that assumption, the whole assumptions of economics, the mathematics of economics breaks down. So I understand why people might be a little bit dissatisfied with it. There are some other social scientists who are just interested in a more formal exploration of theory. I'll come on a little bit later, I think, to that. I can't quite remember what I put in the talk. And some people from distributed artificial intelligence who are interested in exploiting social and psychological theory in artificial systems. Now, one of the things that's actually had an awful lot of debate, certainly in the early days of agent-based modelling, is what is an agent? And to me, this is my answer, not a general one that we generally accepted necessarily, is that agents should not be confused with software agents. There are some people who do agent-based social simulation with software agents, but I don't think there's any need to. And all I'm concerned with is that there is an explicit representation of an individual, which may represent a person or a part, or they can even represent collections, small collections of individuals, depending on what the model's for, like households, companies, or governments, in a simulation. And you're also representing their interactions. And there are numbers of different kinds of agent-based social simulation. The Journal of Artificial Societies and Social Simulation, which that reference is from, has an article sort of describing them. And they kind of start off with the theoretical abstractions, which are very common in the early days of agent-based social simulation. People taking very simple models and drawing quite general conclusions from them. But one of the earliest ones was done by someone called Schelling. And apologies to those who are red-blue colour, but this is the kind of default colours that are provided by the model. Now, Schelling actually did this model on a checkers board in the 60s. And what he was trying to do was look at if people have only a mild preference to be with or be near people who are like them, what are the implications of that when they come to move house? So we start off with an initial random distribution of households among red and blue. We give them this little mild preference, and then we play the model through, and you actually end up with quite a segregated space over time, and so it's quite a sort of interesting result. So that's kind of this theoretical abstraction. There's no great sort of cognitive capability going on underneath in the agent's behaviour. You just have these very simple rules. We then move on to typifications, which kind of models covering a class of system. So an example is the model I've worked on called Fearless, which is an agent-based model of agricultural land use change, which, working at the James Hutt Institute, is the sort of thing I should be doing. And then you can get, if you like, the instance equivalent of that class called case-based models, where you have models fitted to a specific system. Now, one of the advantages with typifications is that you can kind of simulated at an abstract level without actually ever getting specific about any one case study. And of course, the disadvantage of that is that you sometimes have an argument about how applicable your findings are to the real world. Case-based models, by contrast, you've got a real problem finding data. Agent-based models, certainly in the case-based case, are extremely data hungry because you need a lot of information about individual people and how they interact and what their circumstances are. And that can be very difficult to come by. Moving on to computational constraints, I've just mentioned availability of and access to data. There's also a data issue associated with managing simulation output. Particularly in the kind of modelling I do, making lots of runs of the model, you can end up with a huge amount of data that you need to process. I say huge, people talk about terabytes now, but I mean sort of tens or hundreds of gigabytes. Yeah, you've got the problem of data, which is, how big is your hard disk, how much data can you fit on. You've got size and scale of simulation, both measured in terms of numbers of agents and number of interactions. Obviously, the more interactions, the longer it takes the simulation to run, and the larger number of agents, the more memory you need. Then there's also sort of coverage of parameter space and ability to explore the model's behaviour. When you do this kind of modelling, you don't tend not to just run the model once and see what the output is. You have stochastic components, there will be parameters that you can't get from the real world. So you need to try different parameter settings, different scenarios to see what the model's dynamics are like. And so for the three kind of classes of simulation model that I discussed earlier, I'm going to look at the three constraints I've talked about here and come up with this matrix. So just why do these things matter? Well, here's some work I did with my model, and I was just interested in what happens when I increase the number of agents. And I'd done some work before in which we had some agents. Each cell, let's pretend each cell is an agent, and it's copying the land uses, which are just represented by a colour, of other agents in its immediate neighbourhood. So it could be in the 8 cells around it. And what we call pure imitative strategy, their choice set consists of only the land uses in the neighbourhood. There might be other strategies that they sometimes copy, or they sometimes choose at random among the whole set of land uses that are available, so that can bring in land uses that aren't in their neighbourhood. I'm not saying real farmers behave in this way, it's just sort of an interesting problem. What can happen when you've only got pure imitative strategies in the way that decisions are made is that land uses can become extinct. And in the end, you end up with only one land use left. So this is kind of the evolution of the system over time, initial random distribution of land uses, and gradually you kind of get these clumps forming over time. If you see the yellow colour pretty much has disappeared, I think, by then. And in the end, you end up with just one. That can run on for quite a long time sometimes. That run just happens to be a relatively short one. So one of the things I thought was, well, what are the distributions of lock-in times when you've got pure imitation? We call lock-in this point where you reach everybody having the same land use, as you increase the size of the space and hence the number of agents. And sure enough, 7 by 7 you're locking in very quickly, and by 250 by 250 you end up with most of the simulations not locking in during the time period of the simulation. That's not to say they would never lock in.
Sorry, what's the lock-in time?
Lock-in time is how many time steps does it take for the simulation to reach the situation in which there's only one land use. Yeah. So the point is that any conclusion I'd done, based on this simulation, in which we've only got 7 by 7, we've got 49 agents here. Any conclusions I might have reached based on this simulation, if they related to lock-in time or to the phenomenon of lock-in at all, don't generalise to a situation in which you've got this number of agents, whatever that is, about 60,000 or something. And what's interesting about that number in the bottom right-hand corner is, depending what you define as a farm, there are roughly that order of magnitude of farms in Scotland. So the general point is that conclusions drawn for a small number of agents may not generalise to a large number of agents. And so that if you've got a computational constraint that means you can't simulate with a large number of agents, it may be useful to try and overcome that constraint to see if your conclusions generalise. So that's the general point. And then we can look at parameter space. Now, in 1986, a chap called Robert Axelrod studied the emergence of cooperation in a population playing a game. Basically, each agent just has a couple of choices. They can kind of cooperate or defect. If they defect, there's actually a kind of incentive for them to do so. You get a payoff from what you've done. There's a kind of incentive for you to defect. You always get more by defecting than you would by cooperating. What he did was to give agents the option of punishing defectors, so that then you take away some of the gain that they've made by defecting. But to punish someone kind of is a small cost to yourself. And he found, he basically threw a genetic algorithm at it. He had a sort of probability of defection and probability of punishment. And he found the only way he could get cooperation to emerge most of the time was by introducing meta-norms, which was punishing agents who didn't punish others. So you had not only the need to punish agents who defected, you've also got to punish people who don't punish others. Now, 1986, computers didn't have a huge amount of power. The average calculator probably has more power now than a computer did then. And he only was able to run his model for 100 generations, and he didn't explore different model parameter settings. And then some work by a couple of researchers from Spain showed that the long-run dynamics reversed Axelrod's findings. So this is Axelrod's finding. The green curve, what I'm expecting to see is green and red. So green's on top for those of you who are colourblind, red on the bottom. Normally you get norm establishment, and that's within 1,000 generations there. But if you run it for 1,000,000 generations, the green comes up there and then drops right down. And so the norm is actually for the emergence of cooperation to collapse in the long run. The other thing they did was to play around with the parameters for meta-norm punishment. So this was the cost of punishing someone who hasn't punished someone else, and the amount of punishment that that person got as a result of you punishing them. And by using different parameters than Axelrod used, they found that norm collapse was more common in a relatively much shorter time period. So this is within the kind of time period that Axelrod was looking at. Again, from this we learned that conclusions drawn from one set of parameters or for a restricted time period may not generalize to other parameters and the long run. Which is why you need large-scale social simulation to check if your conclusions are generalizable. And it's all about various ways in which we need to be able to scale things up. So the problem of exploring different parameter variants is all about enabling multiple runs of models to allow us to explore parameter space, to try algorithmic variants. Now, in social science, unlike in physics, there's this term physics envy, because everything for physics is so much more certain. In social science, there isn't one way to do anything. So there isn't the way, for example, one way to simulate the way agents make decisions. There's a huge plethora of algorithms that people use. Some people use simple heuristic algorithms, which is mostly the case in what I've discussed so far. Other people use things like case-based reasoning, neural nets are used, genetic algorithms, or if you like, memetic algorithms are used. So there's quite a plethora of ways that you can simulate the ways that decisions are made. And the choice of them is kind of arbitrary. So we should probably be trying different ones to see if they make a huge difference. Trying different scenarios. So there, for example, if you want to run your model into the future, there may be some driving variables in your model, things that are kind of not included in the dynamics of the model that might affect the way it runs, and you can develop scenarios for those variables, like time series over time, and see how the model plays out. So the more of those scenarios you can try, the more robust you can prove an intervention to be. You can also increase the sensitivity of experiments, because by making more runs, you're better able to statistically determine whether some intervention in the model has a significant effect. And this problem is embarrassingly parallel. I mean, each run is self-contained. It doesn't need to talk to any other run. So you can run them in parallel, but it's trivial that we should be running this on the cloud. And it's a significant issue for typifications. If you're modeling a class of system, then you do need to try lots of scenarios, you need to try lots of parameters, because you haven't necessarily got data to explore it. Scenario size is a little bit more challenging, and we could call that, if you like, large-scale distributed social simulation. There are a number of authors working on it already. This is by no means an exhaustive list. It is mildly embarrassingly parallel in that each agent could have its own thread or process. But there is the challenge of managing agent interactions across node boundaries. And I'm sure there will be an interesting study to look at the feasibility of sort of distributed social simulation in the general case, because the topology of the interaction of the network of agents is going to affect the feasibility of doing it. I mean, if you've got a fully connected network of a large number of agents, then your network, your physical network topology that's connecting all your nodes together is going to be a significant bottleneck. And it could also cover sort of simulations using or generating large amounts of data. Just an afterthought, really. So, distributed computing has got a lot to offer agent-based social simulation, for all the reasons I've said. But there are numbers of obstacles to its wider use in the community, some of which I've discussed in the plenary session earlier today. A significant issue is that legacy agent-based modeling software is based on non-distributed libraries, so very difficult to kind of split a simulation across nodes. There is now a library called Repast HPC, high performance computing, which has just recently been made available to enable you to do that. Besides that, there are some institutional issues, a lot of bureaucracy. I mean, a lot of institutions, they try and make it easy for you to use their services, their national grid service, they try and make it easy. But still, if you're in your office of any given day, going through the process of getting a grid certificate, it seems like a lot of hassle relative to just buying your own computer and trying to do what you can with that. And people do prefer to own their own equipment rather than buying time with it. For one thing, you've got the issue of repeatability. At least you've got the kit there, so if you need to rerun an experiment, you can do it rather than asking for more money, for example, so you can take it onto the cloud. The unpredictability of research working makes costing CPU time difficult when you're writing a proposal. So if I'm writing a proposal, I'd probably rather put 30 grand in for a really fancy bit of kit to run my simulation on than put 30 grand in for cloud, even though possibly 30 grand for cloud computing might buy me more computing time than my kit does, just for the kind of sense of security it has. There are technological issues. There are some issues with installing prerequisite software on the grid and cloud, which I'll just cover very briefly in a minute. Access to cloud requires technical know-how, which not everybody has, and computer scientists keep changing their mind. So, for example, 10 years ago, everyone was talking about grid, and now some people are saying the grid is dead along with the cloud. Well, what are they going to be saying in 10 years' time? If I invest a huge amount of effort learning about the cloud and getting all my stuff to run on the cloud, and in 10 years' time computer scientists are talking about something else, I'm going to be really annoyed. There are issues there. And so you end up with these approaches to large-scale simulation, relying on Moore's law. If I wait long enough, I'll get the computing power and just buy my piece of kit. And you've got some people now using these big multi-core graphic cards to run social simulations on. So here's my model. It's written in GNU Objective-C, which sort of traces its roots back to the Next platform in, I think, the late 80s, and uses the Swarm libraries, which were, at the time we were developing, pretty much the only libraries for doing agent-based modeling with. Installation is difficult. When I used to do installation, I don't have to do it anymore, but when I used to do it in the early days on a Solaris machine, it could take me up to 2 days. And the reason was there's a huge amount of prerequisite software required by these libraries, and they could actually be sensitive to specific versions of very commonly used tools like SED, TCLTK, Make, GCC, even tar. And sometimes you didn't find out that it had this sensitivity, and you've gone through all the way through the process of compiling all the libraries, running all the prerequisite software, then compiling the libraries, and then trying to run the simulation. And that's when you would find out, you know, via a segmentation fault or a bus error or something, that there was a problem in the compilation process. Now, virtualization is the obvious solution to that, but if I want to do it for free on the grid, then we've still not really got cloud virtualization services in the grid ready yet. Well, I think that'll be ready soon, and then I can stop complaining about it. But experiments are typically CPU and data intensive in my model. In a recent experiment, I made 20,000 runs of the model. Each one takes 10 to 30 minutes. I explored around about 1,000 different parameter settings and generated about 120 gigabytes of data. So, in terms of requirements for distributed computing, the social simulation community differs from typical grid cloud users. I mean, I'm not an expert on the history of the grid, but I think a lot of it came out of the CERN laboratory, where you've got physicists wanting to churn through a huge amount of data. A lot of them are very computer savvy. I happen to have a background in computing science, but I'm having a kind of, I'm saying this on behalf of the sort of agent-based social simulation community I belong to. And your typical agent-based social simulation person has less likely to have expertise in programming. They might be able to do some simple programming in a reasonably simple language, but they're not going to want to invest a huge amount of time learning stuff they don't have to, and particularly if that stuff isn't directly related to designing and running their model. And in fact, a lot of the effort in agent-based modeling toolkit development is all about minimizing programming and maximizing modeling. So there's a website, Modeling for All, which is based on NetLogo, that is designed to help people put models together. And Repulse Symphony, that now is kind of plugged into Eclipse, and they try to help you put models together using flowcharts or diagrams, because these things are more intuitive to some people. Budgets for social science work tend to be a little bit smaller than in some other sciences, and so the money does need to be spent doing the modelling and not learning technologies without a direct relevance to that. And simulations may not have predictable resource requirements, and that's, I'm going to retreat to the sort of complex systems argument there. But it is true that when you run a model, if you've got interactions going on and that network is dynamic, then obviously your CPU time depends on how the connectivity in that network changes over time. The more interactions you've got, the more CPU time you use. It's not necessarily predictable. So that leads to some fairly simple requirements: ease of use, and indeed preferably transparent. You know, if you just design your model and run it, I don't want to know where it's being run, I just want it to run. Accessibility with minimal bureaucracy, and flexibility, because it's very difficult to estimate CPU time and resource needs. We had a go at this using Kepler. This was with some colleagues at Aberdeen University, Eduardo Pinotti and Pete Edwards, in the Swarm Cloud project. And this is the kind of thing I'm talking about. We've used the Kepler workflow tool, which again, well, I'm pleased Paul Watson did this, because it shows workflow. It just highlights that workflows are popular. But this is the bit where something goes off to the cloud. And you know, again, I don't care about it. What I care about is the model, the parameter settings, and processing the results at the end. So to summarise, agent-based social simulation involves the explicit representation of individuals and their interactions. There's a spectrum of the area associated with differing computational limitations. The computational limitations are important because they can affect what you report as the results, and large-scale social simulation aims to address them. Facilitating access of the agent-based social simulation community to grid cloud services, I think, an important part of this, or whatever comes after grid cloud. But the social simulation community have different needs than other typical users of such facilities. That's it.